So the plan for today is pretty simple. I'm going to talk about the next chapter, which is very short because, in my opinion, it goes into a lot of unnecessary detail. Then I just want to demonstrate some projects. We'll do binary games and a couple more projects. And people complained that the projects were too easy, which caught my attention. So you'll find a whole bunch of harder ones added. And I got another one that I spent about 6 hours working on. I haven't solved it myself, but I have a plan. We'll see if I can improve it, which is good, you know. This is what and like I say, the advent of code every year goes through this course, essentially. Exactly this course. They start out with really simple problems, and it gets harder and harder until you have to start using advanced data structures, and then it goes until you have to start using advanced algorithms. And I've never made it to the end. But this course gets you up to about day 15 or 20 of the advent of code, so there's a huge reservoir of very interesting projects to demonstrate it. Anyway, and I'm glad to do it. And they already caught me once. I keep using old-fashioned techniques from like COBOL and Fortran instead of Python, and the project I got up to, you can't do that way. You got to do it in a more modern way. So that's part of why I wanted to teach this course. It helps me up my game to enter the right millennium. Yeah.
Is it the majority complaining, or just a couple of people complaining?
Oh, a few people complain. That's why. But I'm hopefully, you know, if it's too hard, let me know. That's why I try to make it so there should be an easy part, which is enough to succeed in the course, and then advanced parts for the students that are ready for them. Yeah. That's why all my courses are structured like a capture the flag contest. I don't expect you all to learn the same amount of stuff or reach the same point. All I want to see is that everybody makes some progress from where they are. That's why I'm glad to have that kind of freedom when I'm teaching a course that doesn't have a certification exam at the end. I don't have to make sure everybody's synchronized.
This is the first time I see that in a class.
Yeah, but anyway, there's a bunch of new ones there, and I'll keep them coming. Anyway, so let's take a look at the chapter, which won't take all that long at all. All right, and let's see if I've got it filling the visible area of this projector. Yeah, it's about as good as it's going to get. Okay, so an algorithm is just a well-defined procedure, as I think you all know, explaining how to take some input data, process it, and produce some output. And unless you get into machine learning, which by the way is wonderful and fascinating, and I really want to teach a course here in it, you have to plan the algorithm. Machine learning makes up their own algorithm, which is very nice, very interesting. And I've got a whole course ready to do that as soon as some college will approve it. Till then I'm teaching it as unofficial courses and at places like DEF CON. Anyway, so performance analysis is a big point of algorithms. If you have a smart algorithm, you get the job done with much less resources, much faster, and it's consuming less memory. And this is what keeps getting me, because my natural algorithms are from like the 1970s in languages like COBOL that did not have any of the advanced techniques. So I've had CTFs I've got into where they say, solve this problem, and I can solve it. They say, okay, now solve it 10 times faster, and then 10 times faster. And I can't do that with my old-fashioned techniques. But you can if you understand the modern techniques. So anyway, you should understand how to rate programs. And so let me just run this one. I've saved the text here so I can run it live. So let me get this going. I want my Google Colab, and I've got to sign in, and then I've got to drag it to a better part of the screen. Get into one of my accounts here. All right, and have a new notebook. And apparently this is the visible part of the screen, and so it is. All right, so here's some code. Whoa. Let me try again to copy it from the slide here. All right, oh, I see, something bad happened. All right, A, C, there we go. V, there we are. All right, so I import time, and now I'm going to take n is 10 to the power, and I'm going to do a, just calculate a total here, calculating the total of all the numbers up to a certain point. Let's run this and see. All right. Launching. Okay, there we are. So the point here is, here's the number of numbers I count through, and as you can see, if this goes up by a factor of 10, the time goes up by a factor of 10. From point 0002 to 002 to approximate 102, then 0.2, then 2. That's linear in time, and this is a common arrangement. If you have, and this is the amount of time it would take, for example, to find something in an unsorted list. If you have an unsorted list and you're hunting for something, you have to just compare what you're looking to, the so-called needle in haystack is what they say, you're looking for a needle in a haystack. You take a needle and compare it to each item one by one until you either reach the end of the list and you didn't find it, or you do find it. So if you do find it, that will take an average of n over 2 steps. And if you don't find it, it'll take an average of n steps, exactly n steps. So if you increase n, it'll grow linearly with n. This is the sort of obvious, any kind of simple algorithm will have this property of scaling linearly with n. And this is the way you rate the efficiency of programs, is by how fast do they grow when the problems get big. And same thing's true of everything, including machine learning. And some problems, like simple physics problems, we don't have to handle a large number of data items, but in machine learning you always do. And in the modern world, a lot of problems use big data, and so it really matters to worry about how things go. So here, the only one I ever heard of and the only one I've ever used is big O. This is what everybody uses, big O, which is the worst case with an upper bound. That's enough. You say it's order n squared, order log n. That's how you specify how good your algorithms are. In your book, they define a few others I've never seen actually used. The worst case running time with a tighter bound and a lower bound of running time, omega and theta. But the only one I ever hear of is big O. And in practice, they should all be pretty much the same. So here's various time complexity, and here they are in order of size. So constant does not depend on the number of input elements. That would be very nice. Logarithmic is the smallest possible dependence on input elements. Every time you double the number of input elements, it just takes a constant amount more time. And we'll see some of those. That's like a binary search. This is extremely efficient. Linear is what I just showed you. That's simple, and it's not too bad. Then n log n is the multiply of n times log n, so it's faster than n, but not much faster. And then n squared, n cubed. And the worst is 2 to the n, and the electronic version of your textbook doesn't seem to understand superscripts. That's not 2n, that should be 2 to the n. And there are a lot, and that's what most cracking cryptographic puzzles are like. If you have a 128-bit key for AES, you have to do 2 to the 128 operations to crack it, and there are not enough atoms in the universe to do 2 to the 100 calculations in all the time there will ever be. So if anything really takes 2 to the 100 steps, that is impossible. It will never be done. And that's what you want in cryptography. You want getting in there without the key to be impossible, even if you had the biggest computer you can afford and the most time you could have. And that's why this is so important, especially in the world of cryptography. In cryptography, you use it to prove that certain things are impossible, and now you know it's secure, because the bad guy attacking you would have to do something impossible. And in productive programming, you consider these things so you can plan algorithms that are going to be efficient enough to do the job they need to do. So if you have a lot of terms, like part of your program is constant, part of your program scales linearly, part of your program scales as the cube, if you're familiar with physics, you know this, that's where I learned it, you can forget all these. For large n, only the biggest term will matter. The rest of them are negligible. This is order of n cubed. It's not intended to be an absolute exact measure. It's intended to show you in approximately how it scales, so you can rate algorithms. And you don't care about the 4, just that it grows as the cube of n is what really matters. All right, so here's one with order of n squared complexity. Let me run this one. All right. All right, so this one here, I'm going to go from 2 to the 5, going up by 10 to that power. And now I just go through 2 loops of range n. So this is like a 2-dimensional problem. You have to search through n items, and then you have to search through another n items to get the job done. So that's going to scale as the square of n. And so 100 is 0.02, 1,000 is 0.2. Take away 2 zeros. Each power of 10 increases the time by a power of 100. So this one should be taking about 3 seconds. Or well, about 30 seconds, I guess, yeah. And the next one will be like 300 seconds. So that's n squared. A lot worse than n, as you can see. And all right, and here's 2 to the n, which is what it would be to break into most forms of encryption without knowing the key by trying all possible keys. So here, I'm going to have 2 to the n, and I'm going to go through a range of items here, and I'm going to run a loop 2 to the n times. And this is n, so it's going to go from 2 to the 15 up to 2 to the 25. And I just chose those numbers to take a reasonable amount of time so we can measure that and it doesn't take too long to wait. And so here, every time you add 1 to n, you approximately double the time, 0.02, 0.04, 0.10, 0.20, 0.40, 0.8. So you see, that's what cryptography is like. Adding 1 more bit doubles the amount of time, and that's why 100 bits, anything longer than 100 bits is effectively unbreakable. Although, I should mention for completeness that if you have a quantum computer, there are a couple specific algorithms that get weak, and AES, the most common algorithm everybody uses, is broken to slightly by a quantum computer, you can crack a 128-bit key with a quantum computer with only 2 to the 64 operations. So you have to go to 256-bit AES, and it would take the quantum computer 2 to the 128 operations, and that would still be more than you could ever do. And of course, this is only theoretical. There are no quantum computers that do anything even remotely worth doing right now. They're all too noisy and primitive. Everybody is just imagining if they keep improving, in 20 or 30 years, they'll start to be able to crack our cryptography. And that's why we have to move now, because it's not acceptable if the stuff you've encrypted becomes exposed in 20 or 30 years. That could be medical records, it could be insurance records, financial records. Even if it's broken in 20 or 30 years, that's still not acceptable. So everybody is moving to post-quantum cryptography, which cannot be broken even on a quantum computer. Anyway, all right, so Bitcoin is very handy, by the way, if you want to make these statements like I've boldly been making, like how many bits it takes to be secure, because Bitcoin is a measure of the entire computing capacity of Earth. Bitcoin has the property of paying people if you have the fastest computer and you win the race. Every 10 minutes there's a race. People draw a lot of lottery tickets and somebody wins and they get a Bitcoin if they win. So if you can print more lottery tickets faster, you have a higher chance of winning. So there's a financial incentive to build the fastest computer you can run, and many people are doing it, and that's the total Bitcoin hash transaction is a measure of the computing power. And so the way it works is they constantly adjust the target block, the difficulty, to make the mining time 10 minutes. So if people get tired, for example, China outlawed this a few years back, so suddenly the power of the Earth's Bitcoin computers went down. So in that case, it would lower the difficulty so that remaining computers can still solve it in 10 minutes. And if more people join with faster computers, they'll make the difficulty harder to keep the block mining time at close to 10 minutes. And so here you see some examples. When Bitcoin started in 2009, this was the number. It's a 256-bit hash, and all you have to do is calculate the hash of a block, then add a nonce to it and keep calculating that hash until you get a hash lower than this value. So that would be, looks like about the first 8 or 10 bits of 0. So you'd have, that's relatively easy. By 2012, you can see it was much harder. Every 0 here represents 2 to the 16 times harder. Or 2 to the 4 times harder, 16 times harder. So this is a lot of 16s, they're a whole lot harder, and here it is now, even harder again. More and more people with more and more powerful computers are mining Bitcoin. All right. And so here's another measure of the difficulty. They have a strange scale for measuring the difficulty, but the main thing you can easily see is as the years go by, the difficulty pretty much monotonically gets harder and harder because people, of course, invent faster and faster computers to do this job, and as they're making real money, they invest. What they do is they migrate to wherever you can get the cheapest electricity. It turns out the limit is power. And so usually one popular solution is to move to a country that is corrupt so you can like bribe somebody and get free power. There's various techniques. Yeah?
Also nuclear power.
If the nuclear is cheap. All that matters is a lot of power for cheap. Yeah. That's right. And they moved to all different places. All right. Now this is why, by the way, Bitcoin is technically a failure. The original purpose of Bitcoin was to create something. Bitcoin was created by political activists who objected to the devaluing of the London pound after the 2008 financial crash. In 2008, the UK government and the US government allowed mortgage lenders to make ridiculous bets, loan money to people who they knew would not be able to pay it back, and then when all those people couldn't pay it back, they all were going to go broke to an extent that it would crash the financial system. And so the financial government of the UK and America made really drastic, outrageous decisions to change the money supply in order to prevent the financial system from crashing. And the old-fashioned economics, following the Austrian School of Economics, feel very strongly that you should not do this. They followed a model I used to believe too, because I was from physics, that money is just like water. And if you just dump a whole bunch of extra money out there, it will devalue the money because you're just diluting it, the good money, with a bunch of worthless money. That turns out not to be true. Apparently Keynesian economics is true, that money is like happiness, and if people are happy, everything's fine, and the actual amount of it doesn't matter as much as you think it does. But anyway, people who believed this felt like this was a terrible mistake. It's going to kill the economy to just print all this money, and therefore we should never do it again. Therefore, he said, we should have a different currency that can never be devalued. And Bitcoin is that currency. It was designed to have one property which succeeded, which is there are a total of 21 million Bitcoins. There will never, ever be any more. After all the miners have mined all the Bitcoins there are, that'll be 21 million. So there's no way for anybody to print more or remove them, and no government can control it. Nobody can put a national border on it. Nobody can outlaw it effectively. If you have access to the internet, you can get to it. And until they bring down the whole internet, if there's one miner still running, it exists. So that was the idea. They've created a hard currency that can't be forged, can't be diluted, can't be blocked by any government law. That worked. But unfortunately, the plan to make that work, he wanted to make it so miners would be distributed around the world. And the problem is, this is a mistake. Since all Bitcoin does is calculate SHA-256 of SHA-256 of a block of data, that does not require much memory. All that requires is CPU time. So the only thing you need to mine Bitcoin is a fast CPU. That had the result I described, that after a while, the only thing that mattered was access to a lot of power. So in fact, almost all the Bitcoins were mined in China for a while. Now I think they're almost all mined in USA. They move around where they're mined. But he wanted to have a geographical distribution of it everywhere so everybody's contributing equally to it. And that was a massive failure. Due to a poor design, it ended up being concentrated. And I think I have, here's the latest country list of what countries are mining Bitcoin. And as you can see, the dark red is the area. And pretty much it's all the US now, with a couple places over here. It used to all be China before China outlawed it. And that's not the goal. He would like to see this uniformly spread around the world, and probably Ethereum would be that way if they were still doing this kind of mining, because that's memory hard. Yeah.
When do you think the world currency is going to be the digital?
The world currency?
Yeah,
Well, I think the world currency, amazingly enough, is still the dollar. All of our so-called financial problems here are nothing compared to the rest of the world. The dollar is still the most trusted. Bitcoin turned out to be a lot less stable and a lot financially less valuable. I think Bitcoin served as an experiment to prove Austrian economics wrong, because when the dollar went down in the pandemic, Bitcoin just went down with it, and that was not supposed to happen. Bitcoin is supposed to be a trusted reserve currency like gold that would stay up even if the dollar crashed, and it's not true. That's why I say it appears that Keynesian economics is right, that money is not supply over demand. Money is, if people are happy, then they go out and spend money and they feel good about their job and everything's fine, and the supply and demand don't really matter that much. Yeah.
I think that's kind of where like the decentralized part becomes a problem, where a lot of investors, a lot of economic people, compared to say like computer science majors, computer scientists and everyone in that field, love Bitcoin, love to back it, but the finance side, where it comes from, especially government, if there's nothing backing it, there's no like credible source, air quotes,
That's right.
They're not going to value it.
Well, no, it's valued fine, and value does go up. And that was an issue, that it's not backed on anything, but it is backed just by being rare. For example, gold. Gold is not really that great. Why is gold worth so much? It's just a standard of transaction. People trust it, people value it because it's rare and hard to get more. And that was the idea. If you make something rare, it will gain value, and that turned out to be true. And it gained, however, to be fair, it gained value because of two types of transactions. The number one transaction is crime. The main reason people use Bitcoin is to break the law, either money laundering or buying forbidden things like drugs and guns. Or the other thing that matters is money laundering. Money laundering is the main one. So you either buy forbidden products, or you're in a country like Argentina with a terrible currency, and it's safer to move your money into Bitcoin, even though it's very wildly oscillating. So, those are the main reasons it exists. But it turns out that it does have value. People do move into it because it has, and now it has gained a status as a currency like any other. Just like you might move your money into yen or Deutschmarks, you could move them into Bitcoin. It's just another currency like the others. It doesn't based on anything. By the way, another example is Tesla. Tesla is a meme stock. Tesla, at its current valuation, is worth more than all the other car manufacturers put together. Now, that is completely insane. Even in an area like this, if you go out in there, it is not true that half the car is Teslas. It's more like 5% of the car are Teslas. So how can Tesla alone be worth more than GM and all the other car makers put together? It's not, because Elon Musk constantly stays in the headlines by doing something outrageous every day. People just see him as a celebrity, like Donald Trump, and they all assume that being on his team is worth a lot, so they bid his stock up to like 10 or 20 times what it's actually worth. And just like any other celebrity, like Taylor Swift, it stays up there as long as he can stay a celebrity, which is what Hollywood people have always done. If you can somehow make people love you and keep them loving you, then you're very valuable. When you get boring, then suddenly your value drops. And it's not based on a financial calculation of profits over expenses. It's based on the less tangible thing, like how much do people love you and adore you? How much do they think you're wonderful? But Trump's doing the same thing, selling NFTs and stuff. As long as he's famous, they're worth a lot of money. When he's not famous, they'll fall. But anyway, All right, so I think, oh, we got a little more here. All right, so I mentioned Ethereum is memory hard. Ethereum was invented later by a guy named Vitalik Buterin, and it was intended to fix the problems of Bitcoin. And it fixed two problems. One is that you can't easily use Bitcoin to perform calculations and algorithms. It's pretty much just a currency. Ethereum is designed to run code on the blockchain. So you can have programs running. The other thing is it was designed to fix this problem I described about distribution. It uses something called a directed acyclic graph, which must be regenerated. An epoch is the time before they award of a block before you award a mine, and the miners have to start over. That's called an epoch, and in Ethereum, it's every 15 seconds, as opposed to 10 minutes for Bitcoin. And the DAG is currently 5 gigabytes. So every 15 seconds, you have to recalculate something that is gigabytes of size, so it takes a lot of memory, and that's intentional. So it is not dependent on CPU, it's dependent on memory, and that is something that's probably equally available pretty much everywhere, and therefore, in principle, the mining would be shared among many other countries. However, about 2 years ago, Ethereum switched from this proof of work to proof of stake, so this all ended, except for the original Ethereum, which is still running, because you can never stop it. Remember, the whole point of these blockchains is nobody can stop it. You can say, I don't like it, and you can quit mining, but as long as there's one person on Earth mining, it's still there. So even when the official Ethereum project says, okay, we're changing to something different, they say, fine, you go ahead and change. I'm going to keep doing the old one. And now there's two kinds of Ethereum. That's what happens, the old, the classic, and the new. Anyway, and there's the mainnet statistics of who's mining it. And it appears to be pretty concentrated right now in a few places anyway. So as far as geographic dispersion, it doesn't really have it. But in principle, it was a pretty good idea. Now it's proof of stake, so what it is the richest people mine, which, by the way, gets very close to the old fiat money standard where you use things like dollars, and the reason you trust them is because the US government is powerful, or you use Visa and MasterCard, and you're trusting Visa and MasterCard to do all the calculations. The rich person says it's true, and you just go with them, which is, basically going back to the old nobility model. Anyway, let's try a Kahoot. I should have those for this chapter 2, just take me a minute to get there. Oh, and I should check and see if there are comments in the Twitch. Just a couple highs, okay, fair enough. All right, might be in my favorites. It is, all right. Good. Anyway, I don't recommend investing in cryptocurrency, but they are very interesting in terms of cryptography, and you can get jobs programming them and securing them. I've got students that did that. If you help build them and maintain them, there's jobs there that do not depend on the madly fluctuating value. Investing in them, you probably do better to go to Vegas and play roulette. But if you're the programmer, you get paid whether it goes up or down. And the security problems are enormous. If you're interested in security, there's many companies doing information security for blockchain companies, and boy, they need it because they get hacked right and left. They're not easy to secure. Primarily because of North Korea. And North Korea has a very effective way to hack you. They trick you into hiring some of them on your staff, pretending to be for somewhere else. Now they're on the inside. Now they can totally find out how to steal your money. It's very effective. It works. They're funding their entire military with stolen crypto. Which is why a lot of Square people say you shouldn't even have this stuff, but whether we should or not, we do. All right, so what's the lower bound of running time? That's omega, apparently, all right? So what's the time complexity of that code there? Couldn't put the carriage returns in this format. grows with n. It's going to print a word n times, so it grows linearly, order of n. If n goes up by a factor of 10, the time it takes to do this will go up by a factor of 10. All right. All right, how about this code? I have a loop going up to n, a loop going up to 10, and then I print. I should probably have made images with proper indentation. Sorry about that. Right, it's still linear. The first loop grows with n, the second loop is constant time. So it takes a certain amount of time to do this once, it'll take n amount of time. This is linear in n. Not a popular answer. People thought it was n squared, but it's not because there's only one n here. So if n goes up by a factor of 10, it'll take 10 times as long to run. All right. And this one, I equals 0, then while I less than 2 to the n, print high. That's 2 to the n. It's a loop, and the size of the loop is 2 to the n. It's going to count from 1 to 2 to the n, so it's going to grow as 2 to the n. That's it. All right, these are very simple examples, but that's the idea. You get used to these different measures of size, of efficiency, I guess I should say. Got the names. All right, so let me stop this recording.